Professor Chaplot, you can start
Yeah.
now. Please.
Okay. Great. So good afternoon, friends. Last time on Friday, we had this tutorial. I hope you found it useful. If there are any questions, please let us know. I believe so far you have not asked any questions on the tutorial or anything. So today, however, we will continue with the previous lecture on Wednesday on the quasi-elastic neutron scattering. And so let's just revise a little bit. Yes. So quasi-elastic neutron scattering, essentially we are looking at stochastic dynamics. And yeah, so that is the stochastic dynamics gives you a kind of Lorentzian functions around zero energy transfer, that is at around omega equal to 0. Omega equal to 0, you have the elastic scattering broadened by the resolution of the instrument. Inelastic scattering occurs at finite energies in energy loss mode or energy gain mode for the neutrons, which can occur at any energy. And the stochastic dynamics occurs around zero energy transfer, which has a Lorentzian-like distribution. It could be something different also, but most of the time it's Lorentzian. Okay. We also said that for typical relaxation times of the stochastic dynamics of the order of 1 picosecond, the width of the Lorentzian function is 0.66 millielectron volt. And typically, yes, this is the range of energies that neutron scattering can be used for. So these are the widths, and there typically this would mean a few nanoseconds onwards. Okay. Yes. So we also said hydrogen has an unusually large incoherent scattering cross section. So the neutron scattering is extremely useful to understand stochastic dynamics of the hydrogen atom, be it as part of a molecule or individually. Hydrogen jumps in a variety of solids like fuel cells and so on. Okay. So typically we said the variety of translational or rotational diffusion or localized dynamics of any kind, this can be studied. And we have the neutron scattering allows you, as you already know, both the spatial information, namely the pathways of the diffusion process, as well as the time scales, which are typically in the range of a nanosecond to a picosecond, or the dynamics in the range of 1 to 10 angstroms. And if you do the temperature dependence of these measurements, you can get things like activation energies. NMR, on the other hand, is a very complementary and very useful technique. However, that is useful for relatively slower processes where the relaxation times are in excess of 10 nanoseconds. And NMR also does not provide you any direct geometrical information. It's only the time Hello?
Can you hear me, Dr. Chaplot?
Yeah. Yes.
You got disconnected in between.
Okay.
But now you connect. Please share. Sorry for I don't know what happened. The students are waiting. I can see that. Yes. Students, please wait us for a few minutes. We'll start once again. Please wait a little.
Okay. Do you know which up to which screen you had?
Yeah, it's come. Your transparency have come. Yes.
Okay. Okay. I just wonder. I mean, up to what point did I? Okay. Never mind. Otherwise, I'll just continue. Okay. I
Yeah.
believe you had seen this.
Yeah.
In any
Okay.
case, it's a
Yes.
repetition.
We can see it clear. Please continue.
Okay.
Yeah.
All
Please
right.
continue. Yes. Yeah. Yeah.
Yes.
Yeah.
Okay.
Elastic, incoherent translation. You
Yes.
can.
Okay. So, right. So you see, in the quasi-elastic neutron scattering, we have a. Or let me just move back a little bit. We look at
You can
the.
one or two. Yeah.
Yeah,
Yes.
we have
Yes.
the dynamical structure factor, which has for the stochastic dynamics an elastic part and the quasi-elastic part. The elastic part comes due to the time average structure. So typically, if you have any localized stochastic dynamics, namely say rotations or reorientations or some local translational jumps between, let's say, two or more available sites only, any localized translational motion. So now, because the atoms are localized within space, you get elastic scattering due to the time average structure. However, if there is a translational diffusion of long range, then there is no time average structure. The atom could be anywhere in space, and so in that case, you don't get the elastic part, elastic scattering. However, in all cases of the stochastic dynamics, you have the quasi-elastic part, which could be in the form of Lorentzian functions, if the stochastic dynamics is a simple exponential decay correlation function. So that in general, the scattering law or the dynamical structure factor has two terms, the elastic part and maybe a sum of various Lorentzian functions. Okay, so again, this could be coherent scattering or incoherent scattering. If the atoms involved are such that they have a good coherent scattering cross-section, then the collective dynamics would be observed. That means any correlated dynamics of correlated stochastic dynamics of atoms. For example, you could have a rotational diffusion in which more than one atom is part of the molecule, and obviously they will be correlated with each other. Or you can have a correlated diffusion motion. So coherent scattering would contribute to that. Single crystal in such a case, in the case of coherent scattering, single crystal can give you a fairly good information, detailed spatial information as anisotropic different directions. On the other hand, incoherent scattering, as we said, this we would study the single particle dynamics. So there is no correlation is not observed, but whatever happens to a single atom, depending on its the geometry as well as the time related information of the dynamics of a single atom would be observable. And in that case, the elastic scattering part has the geometrical information about the nature of the stochastic dynamics of a single particle. So this is termed as elastic incoherent structure factor measured. However, when we look at incoherent scattering in the presence of other atoms which are coherent scatterers, so the structure would, there would be Bragg reflections. So normally, and Bragg reflections are very strong, very intense, and in the presence of Bragg reflections, it will be difficult to see the this signal, which is usually weaker, and therefore we avoid the exact values of the Bragg reflection, the wave vector exactly equal to or very close to the HKL or the reciprocal lattice points. And away from that, there is not really any serious problem, and we can continue. And in general, these functions are fairly slowly varying as a function of wave vector, and therefore, if you miss a few points, it will not really make an important difference. Okay, the elastic incoherent structure factors have can be easily modeled. For example, if you have a two-fold rotation, is a simple form involving a spherical Bessel function, three-fold or six-fold. So there are different forms available, and in fact, the elastic incoherent structure factor as a function of the wave vector would have somewhat different shapes, and therefore it is possible to identify the nature of motions, nature of the geometrical nature of the dynamics involved. Okay, R here is in fact the radius of rotation, so obviously it's a product of the two that matters. Okay, if it's a translational diffusion, then we have simple models, like it could be a continuous diffusion, like in the random diffusion, which means jump lengths can be randomly, it's like a random walk. Okay, so if that kind of diffusion is involved, then the half width at half maximum of the Lorentzian function is simply proportional to d square, q square, and d being the diffusion coefficient. However, if there are jump-like diffusion with a definite jump length, for example, this can be easily worked out. I mean, if you can function the correlation function corresponding to this dynamics, and then so this is a very straightforward method, and the half width at half maximum has this form. On the other hand, if it's not a fixed jump length, but there is a Gaussian distribution of jump lengths involved, then the function is different. So these are different models. Typically, they have been named after, for example, the fixed jump length model was put up by Chudley and Elliott, so that's called a Chudley-Elliott model. On the other hand, the Gaussian jump length model is a Hall-and-Ross model. Random Bob diffusion is just a fixed law that we know. So these are simple models, are already in the literature for a long time. Okay, if you have both translational diffusion as well as a rotational diffusion, as I said, in case of translational diffusion, you don't have the elastic scattering because the atoms could be anywhere in space. There is no localization involved. If you have a localized localized jump motion, then this would be the form. Okay, so this is an unlocalized or not localized diffusion process. However, if both the kinds of motions are there, that there is a molecule which is translating as well as rotating, then you need to one actually has a convolution of the two scattering functions, and so that is how it is done. Okay, we will come back to this later. So now today, so far it was just revising the lecture on the that I had given on Wednesday last. Today we'll specifically discuss the molecular dynamics simulation method, which is a very good simulation technique used for a variety of dynamical or even structural phase transition processes and so on. And it's a very simple technique where you just solve the classical equations of motion of many interacting particles. Literally, these are Newton's equations of motion. So it's a classical technique. Please remember this. Molecular dynamics technique is a classical technique where the atoms are assumed as point particles. Okay, so the particles have a definite position and a momentum, and therefore this is, and we use a classical equations of motion. However, the actual calculation, and once you have a classical equation of motion, we all know that the important quantity that drives the dynamics is the force field. That is how the forces act on the particles. So, so those forces could be calculated quantum mechanically to make the entire process more accurate. I mean, even though it's a classical, we are solving classical equations of motions of nuclei, but the forces on the nuclei can be calculated accurately using the quantum mechanics, and in particular, an excellent technique is the density functional theory. So that can be done. Or alternatively, one could use empirical potentials between atoms or molecules, empirical force fields or empirical interatomic potentials. And then these are useful. So these two techniques are in process. The case when we calculate the forces using potentials is usually that molecular dynamics is called the classical molecular dynamics. Okay, so the potentials are empirical potentials, and we use classical equations of motion. With this combination, it is called classical molecular dynamics. On the other hand, if we derive the forces using any of the ab initio methods or density functional theory or quantum mechanics, then calculation of forces using ab initio methods and solving the classical equations of motion, that technique is called ab initio molecular dynamics. So the term ab initio molecular dynamics is used when we solve classical equations of motion using ab initio force calculations. Okay. So far, this is just for the terminology. However, as you can see, there are not really many other approximations about the nature of the dynamics. We don't assume periodic dynamics, or we don't assume stochastic dynamics only. It could be any kind of dynamics. It could be any kind of structures. You don't need to have only harmonic dynamics or small displacements, or you don't have to assume a low temperature, anything. So any value of the pressure or temperature can be assumed, and there are no further approximation used besides the fact that we use classical equations of motion. So it is possible then to calculate the microscopic structure and dynamics at any arbitrary external stress and temperature. And because we calculate the positions and positions as a function of time, the trajectories of the atoms, and once you have the trajectories, you also have the velocities available. If you have the position as a function of time, you calculate the velocities, and therefore you have all the full position and time information. You can calculate the position time correlation functions as we defined, and the position time correlation functions with their double Fourier transform, you can calculate directly the dynamical structure factor as a function of wave vector and frequency. Okay, so the Fourier transform of position and time correlation function gives you the dynamical structure factor as a function of wave vector and the frequency, and so therefore that information can be directly compared with measurements from scattering experiments like neutron scattering, as we said, also the X-ray scattering, or even optical experiments. A variety of these direct comparison is possible. However, this entire method, although it appears so nice, for the study of microscopic structure and dynamics of atoms or molecules inside the solid, the length scales are limited. The reason it is limited is because using even the best of the computers that we have access to, we can calculate the equations of motions for maybe up to 1 million atoms. Okay, that would still be a very difficult, time expensive or computer expensive process. Typically, the calculations are done for only a few hundred atoms in case of ab initio molecular dynamics, or running into thousands of atoms for the classical molecular dynamics. But in either case, The length scales are limited to about an angstrom to a micron. The lower end is the limitation for ab initio molecular dynamics, and this upper end actually with the classical molecular dynamics, we can approach there. So also, because the time scale of this dynamics inside a solid is typically the time scale of the atomic vibrations. Okay, and the time scale of the atomic vibrations, as we already learned, is in the range of a picosecond. And therefore, the time scale that you can really access by molecular dynamic simulation could be as low as a femtosecond to perhaps a microsecond, because beyond which the calculation becomes again very time consuming. You cannot, because you have to work at the picosecond scale. So even if you repeat the process and solve the equations of motion a million times, you are still going to reach only a microsecond. Okay. However, this is still extremely useful because we know that the actual microscopic processes that take place inside the solid, whether these are phase transitions or any kinds of other stochastic dynamics or periodic dynamics and whatnot, they actually occur within these length scales and time scales. And therefore, it is possible to directly study things like equation of state or phase transitions or a variety of thermodynamic properties which can be studied, like thermal conductivity or thermal expansion, specific heat, and whatnot. And also non-equilibrium processes. That's another very important, that this technique is not limited to studying equilibrium properties alone. One can study the time-dependent properties, like how the defects propagate in a solid, or how, for example, a shock wave propagates inside a solid, causing changes in the structures and also a very strong change in the pressure and temperature as the shock moves on. This can be studied. And moreover, we get a direct real space visualization of the structure and dynamics. So, and because we don't have any limitation on what kind of pressure or temperature we can use in the calculation, as long as we ensure that our calculation of the forces is sufficiently accurate for those extreme pressure temperature conditions, one can really investigate this. You can predict new things which are even beyond laboratory conditions. Okay, so let's start. What are the basic important issues? First of all, we need to choose a simulation cell. What this means is, okay, how many atoms or molecules that we can calculate. Okay, now this could be determined by a number of things. It could be on the base, could be determined by what kind of physics you are looking at. Okay, so suppose all I want to simulate is the dynamics of a single simple harmonic oscillator, which normally you would not calculate, but you can. It's just a single atom moving in a harmonic potential. Then, well, you just look at only one single atom and you have a force field. You can study the how the harmonic dynamics actually takes place. Or even if your force field is not harmonic, if it is enharmonic potential, still you can calculate how the trajectory of the atom would be in an enharmonic potential well, and calculate its all time-dependent trajectories. However, as we said, of course, there are limitations on you would not like to choose a too large a number of atoms in your simulation cell. So quite often what we do for crystal, we choose a supercell of say N1 into N2 into N3 unit cells. Okay, so that means if my unit cell dimensions are unit cell lattice parameters are A, B, and C, and alpha, beta, gamma. So the three vectors are vector A, vector B, vector C. I choose N1 times A star, N1 times A, N2 times B, and N3 times C. So a simulation cell comprising of N1 into N2 into N3 unit cells can be used. Each of the unit cells may have certain number of atoms, so you will have a total number of atoms, which is number of atoms inside one unit cell multiplied by n1, n2, and n3. You may have a total of capital N number of atoms inside the unit cell. Okay, so this is fine. However, there is a consequence here which I should like to tell you, that once you have chosen a certain number of unit cells, and yes, mind you, you have to apply some boundary conditions on it, because if you want to really simulate the infinite crystal, then although I choose a cell which is consisting of so many unit cells, but then on the top of it, over and above this cell, I apply periodic boundary conditions on this cell, which means the positions of the atoms will repeat along, let's say, the vector A after n1 unit cells. Okay. So along vector A after n1 times A distance, the positions would repeat. Similarly, along the B and C directions also. So you apply periodic boundary conditions to simulate infinite systems. If you do not wish to simulate an infinite system, but if you wish to just simulate a finite cluster or a nanoparticle, then yes, you don't have to impose periodic boundary conditions, and then automatically the atoms which are at the surface of this cluster or nanoparticle may have different dynamics or different force field. Depending on the force field at the surface, it may have a different dynamics. I can have partial periodic boundary conditions if I want to simulate a surface or a thin film or a multi-layer system. So then only, let's say, in the plane of the thin film, or I can use infinite periodic boundary conditions, and along the perpendicular to the surface, I don't apply any periodicity. So that is possible. Okay, I could apply periodicity also perpendicular to the surface, but maybe I take a vacuum slab in between. So these are further details. We'll not really go into it here, but so we apply periodic boundary conditions, and then we also start with certain initial positions of the positions or velocities or accelerations for each of the n atoms. The initial positions could simply be the equilibrium positions in the crystallographic cell. And in that case, if I do that, at equilibrium positions, there will be no forces on the atoms. So I must give some starting values of the velocities for the system to start with. So normally one would give some random velocities consistent with the temperature. If I choose certain velocities, VBI, for example, then half mVi square is the kinetic energy which is proportional to temperature. So therefore, what I wish to say is that the initial random velocities are proportional to the square root of temperature. Okay, and one works out certain method to give random numbers which are, so these are chosen on the basis of random numbers, but we make sure normalize the values such that the total kinetic energy is equal to the temperature of our interest. And of course, as we said, forces will be calculated using the whatever force field you have, whether you have a ab initio density functional calculation, or you have an empirical potential force field. Yeah, and mi are the masses of the n atoms, because acceleration is force divided by mass. That is the Newton's equation anyway. Yeah, but I was going to tell an important thing here, namely that once you choose any finite size of a supercell on which you apply periodic boundary conditions, but however, once you have chosen a finite cell and you have employed periodic boundary conditions, that means the dynamics that can actually take place, because it is periodic after n1 cells. So any dynamics which is periodic over n1 cells will mean that the corresponding wave vectors will be limited. You cannot have an arbitrary wave vector. The wave vector, like this is like standing waves you can form, for example, in a box. So in a given box of a size n1, for example, n1 times the lattice constant along the a direction, along the direction of the lattice vector lattice vector a, the length is n1 times a. So in such a box, even though you apply periodic boundary condition, there are certain standing waves only which can be formed, for example. Or well, in this case, they don't have to be standing waves, but the wave vectors that are possible will then correspond to a certain mesh in the Brillouin zone. Okay, so along the A direction, you can have only wave vectors which are n1 times 8 and its fractions. Okay, those kind of wave vectors which are, so it is the, like our Brillouin zone is divided into a mesh of so many points, and only those wave vectors are permissible wave vectors, or wave vectors that are consistent with my periodic boundary conditions on these unit cells. And of course, for example, even if I don't have periodic boundary condition, and if I use a finite cluster, then also depending on the number of, depending on the size of that simulation cell, you can only form certain kind of standing waves inside, and only those wave vectors will have meaning, or equivalently means that only that kind of dynamics is possible. So the main point is, important point is that the wave vectors that are observable will be limited by the simulation size and the number of atoms you have inside this. We will see its ramifications as and when we move on. Okay. So having chosen a simulation cell with certain initial values of the positions, velocities, and then how do we calculate the positions at next time? So typically one chooses a time step, let's say delta t, and that time step determined by the fastest process in the system that you have. So let's say if I'm interested in the periodic dynamics of atoms, or so typically what is the largest frequency of vibrations, and if you have to simulate that frequency, that means my time step has to be smaller, sufficiently small, at least in order of magnitude smaller than the smallest time period. The largest frequency, the largest periodic frequency gives me the smallest time period of vibration, and I should choose a time step which is something like an order of magnitude smaller than that. So these numbers come out in the range of a femtosecond, because typically the largest frequency is maybe like 10 terahertz, or even maybe a few tens of terahertz. So it will be a few tens of femtoseconds will be the time period of oscillation, and therefore typically 1 or 2 femtoseconds would be a good time step. Well, but you can change it. I mean, you can do actual simulations with the somewhat different values of the time steps, and see that the quantity that you're looking for, whether there is a convergence. Okay, so you get a convergence, and then you look at this. So, so you need to choose a time step, and then if I have the, let's say, the position at any time t, then to get the position at time t plus delta t, all I do here is a simple Taylor expansion of the position. So the position rt plus delta t is expressed in terms of rt, then velocity times t into delta t. That's the first derivative of the position, second derivative of the position, and any higher order terms, the third derivative onwards. Okay, I can simply write it in the negative time also, t minus delta t. And if I just, so here this terms will become negative. And then I sum the two. Okay, if I sum the two, then what happens is that the odd order terms will simply cancel. So you will get, and also the third order term will cancel. That is very important, that if I sum the two, I don't get the third order term. And say I'm willing to ignore the higher order terms because my delta t is chosen small enough. I'm not chosen too large a value. And therefore, if I just sum the two and then I can write it like this, that RT plus T is equal to 2 times of RT minus R of RT minus delta T. This terms are cancelled when we sum the two, and this will be summed over. So this is and we ignore the higher order terms here. So the position at time t plus delta t can be determined from the previous positions at t minus delta t and at time t, and the acceleration at the time t. Okay, so this can be done. The velocity can be simply written in terms of the positions at t plus delta t and t minus delta t, and the acceleration directly comes from the force field or the ab initio method. So this algorithm was first given by Verlet, and so it's named after him and called Verlet algorithm. It's a very popular algorithm. Quite often people use more complex algorithms than this, involving not just the previous time, but even many previous times to get even more accurate values. But this works well in many cases, and it's just an example of a good algorithm. Yes, so yes, we did that. Now, what are the various things you monitor? So, for example, I'm interested, obviously, in the total kinetic energy in the system. So, as we just said, if you sum over half mv squares, the v being the velocity of all the atoms, n atoms, then that gives me the total kinetic energy in the system. Okay, so this total kinetic energy is an important quantity that can be calculated. As we know, this is going to be proportional to the total temperature. To calculate normally temperature, we further take an ensemble average over a number of time steps. So, because the reason we do ensemble average is that this value of the kinetic energy of a finite system of n particles actually has fluctuations, which you might understand easily, that is of the order of 1 by root of n. So larger the number of atoms in my supercell, the fluctuations would be less, but this is a simple statistical mechanics result that a quantity summed over n atoms would have the average value would have fluctuations of this kind, 1 over root of n. So, so the actual kinetic energy is actually varying with time, with these numbers, and so also the total potential energy or the internal energy. So I can calculate the total internal energy of at any point in time by just taking this number can be available directly from the ab initio method, or if I use any potential empirical potential, then I can also calculate by taking pairs of atoms in the simulation cell. So I have the total internal energy, which I can call just the potential energy, which would have actually two terms: the average, the ground state energy of the system, plus the potential energy of the dynamics. So, you know, you have the ground state energy, which corresponds to, say, zero temperature, when besides the 0 point motion, there are no vibrations. So that is the ground state internal energy. And the energy due to vibrations or any dynamics. So that will be typically of the kT, of the order of kT, Boltzmann time constant times temperature. Half of that is kinetic and the other half is potential. That is our standard equipartition statement, that the total energy, total energy due to the dynamics of atoms is divided in half potential and half kinetic energy. We will do that. So, okay. So you have the total internal energy, and U also has, as I said, has fluctuations. In fact, to rather easily understand it, suppose if you have only one atom and it's in a is, for example, harmonic oscillator, then I know that in the harmonic oscillator, the total energy is a certain number, but the kinetic and potential energy are not constants, but they vary between 0 and kT, and potential energy also varies between 0 and kT, average being half kT, but the fluctuation is half kT plus minus half kT. Okay, that is so that the total kinetic energy of a simple harmonic oscillator is half kT plus minus half kT as a function of time. So also the potential. That is just an illustration that these numbers will fluctuate with time. But on the average, with time, you can get some. So if there is a time average, you get a better number. So the temperature can be written in terms of the total kinetic energy ensemble average. Actually it's not 3n kT, but you have to subtract the number of constraints. Okay, what do you really mean here, for example, is that we know that the three center of mass coordinates don't move. The center of mass is assumed to be constant. So that means you're imposing a constraint and there is no center of mass movement. So that means 3 degrees of freedom are taken out. Okay, if you applied any other constraints, yes. So therefore, but all the same, typically my an is of the order of a few hundreds. So 3 will not really cause a very large error, and therefore, well, this is important, but still the total kinetic energy is just given in terms of temperature. Okay. Other quantity that I can monitor is the external, is a net stress in the system, which can be a, the stress can be a tensor quantity. However, I'm generally more interested in the net pressure. So what is the pressure equivalent? The pressure comes from the boundary conditions of the simulation shape and size. So if I have assumed a fixed number value of the lattice constants or the size and shape of the simulation box, that is a simulation supercell, what we said, this cell of N1, N2, N3 cells. So this size and shape are already fixed by A, B, C, alpha, beta, gamma, or whatever other shape or size I have chosen. If they are not varying, then it would cause certain external pressure. If those values are determined, can be determined corresponding to zero pressure also. However, there is always certain pressure because of the temperature, which is like an ideal gas contribution. So the actual pressure into volume term in the is related to the temperature term. Mind you, what we are talking is classical dynamics. Okay, and therefore I'm using equipartition. I'm using the ideal gas contribution KT. I mean and obviously in such a case there is nothing like a 0 point energy. There are no excitations. Even if you harmonic oscillators, they are not quantized excitations. Numbers can be continuously varying, and so on. Yes. So this we have to keep in mind, and I'll tell you later on how we can get around this to a certain extent. However, the basic method is a classical equations of motion, or it's a classical classical dynamics. So there is a temperature term, and the stress term or the pressure term will be just the product of dot product of the position. There should have been a dot in between. No, I think, okay, there is a dot, but it's very difficult to see it between Rij dot Fij, and so these are the vector distances. Rij is vector distance between two atoms I and J, and Fij is the force between atom I and J. Okay, so R is the distance vector, Fij is the corresponding force vector, N is the number of atoms summed over, and so you can calculate the net pressure. There's a slightly more involved expression for the stress, but that can also be calculated. Okay, so having done that, okay, so this is just a plot of, it actually is plotted temperature, but no, I just want to see the total kinetic energy as a function of time. So I may start with any number. It could be 0 or any number, but quickly in a fairly short time of the order of a picosecond or so, which could be just a few hundred time steps, or in other words, a something like of a few tenths of the time periods of vibrations. Okay, because if there are vibrations taking place, then the average value of the kinetic energy reaches some average value reaches some constant. However, as I said, there are always fluctuations here, and these fluctuations are related to the finite size of my simulation cell. So these fluctuations are of the order of 1 by square root of n. Okay, so that's a typical plot in a, and this is an indicative of an equilibrium. If my temperature value, that is the average kinetic energy, if it doesn't change with the time, that means I have an equilibrium. That means the average kinetic energy is not changing with time, and so also the average potential energy, which is equal to this, is also not changing, and therefore the system is under equilibrium. Okay, so that's a way to look at the equilibrium process. In a non-equilibrium situation, yes, you know what will happen, so you will accordingly take note of it. So we monitor various quantities like total energy, temperature, pressure, volume. Okay, volume is because actually it's possible to do simulation which you don't have to assume a fixed simulation size or shape. Even your parameters of the simulation box, namely the N1, A, N2B, N3C, and the corresponding alpha, beta, gamma, corresponding to the ABC, alpha, beta, gamma, the latest vectors that we have. And now those quantities can also be part of your equation of motion, in the sense that those quantities can also change as a function of time. And those changes will be determined by what is the net value of the internal pressure or internal stress tensor, just as the positions of the atoms are changed depending on the forces on atoms. The simulation cell is changed depending on the stress on the simulation cell, the stress tensor on the simulation cell. Okay, so it's possible. Those kind of simulations are called a constant pressure simulation, or if you don't do that, then you may just have a constant energy simulation in which you don't disturb the total energy of the system from any external means. That is normally called like a microcanonical ensemble. But let's just see. So if it's a simulation in which you can hold the total energy constant by not supplying any energy from outside, you can do a total pressure, constant pressure simulation in which you maintain a pressure by changing the simulation shape and size, in which case you are obviously supplying energy from outside or taking energy out. So it's no more a constant energy simulation. You can have a constant volume simulation, fine, that is possible. So it can be constant volume and constant temperature. You can have a constant temperature simulation. Constant volume simulation would be similar to the constant energy one, but in a constant temperature simulation where you maintain the temperature, even if it's a non-equilibrium situation, by providing an external thermostat, which means you supply the energy, kinetic energy to atoms from outside, or you take out the kinetic energy. So those are like canonical ensembles where the system is in contact with some external thermal bath. So you have constant volume simulations, or constant temperature, or constant pressure. Okay, density is a simple outcome. And one of the quantities you can also calculate to monitor is just to look at the mean square displacements of atoms. So what are the mean square displacements of each atom? So if it's a simple periodic dynamics, then the mean square displacement will have simple values corresponding to this harmonic oscillator, or corresponding to this periodic dynamics, which the mean square displacement will not be changing with time. Okay, so this is simple. However, if you have a diffusion taking place, then yes, those things will change with time. So, okay. That's really a good book by Allen and Tilsley. Now we have we come back to now what we actually calculate. So the position time correlation functions to make contact with neutron scattering. So the essential contact with neutron scattering from with theory is through the position time correlation functions or the structure dynamical structure factor. So just to remind you again, there are two types here. You can talk of the position time correlation function of a single particle. So how the position changes of the single particle as a function of time. So this is simply the probability of finding the particle at a position r at a time t, given that this same particle will present at r equal to 0 at t equal to 0. So how it's evolving with time. Okay. So you can see that this, you can easily find out from this whether the system is only doing, the atom is only undergoing a periodic dynamics, or is undergoing diffusion, or is undergoing just a rotational dynamics, not a small or a rotational diffusion, or a variety of things. Then there is also a distinct part, which is where you see the collective nature of the dynamics, means how the position of one particle affects the position of other particles. So if a particle is there at time t equal to 0 at r equal to 0, how other particles are distributed at time t in r. So that is probability of finding the particle at r and t, given that some other particle was at r0 and t0 and so on. So this I need to actually write down. So the self part of the correlation function is just a delta function of, say, as we said, the probability that Ri of t, that is ith atom at time t, is at r, given that this was at 0. So the distance vector is equal to r for the given same atom. Okay. And yes, you do an ensemble average. Fine. Or if it's distinct, then yes, we take the distance vector between two different particles and the average. Okay. And again, to remind you, yes, so those quantities, if you do a one Fourier transform of R to Q, then yes, you get the intermediate term for a single particle for the self for the self part of the correlation function. The what you get corresponding is the incoherent scattering term, and for the collective distinct part of the correlation function, you get the coherent scattering term. Both of them are present in a solid, depending on the actual value of the incoherent scattering cross section or coherent scattering cross section of the individual atoms. Okay, so it is just an atomic property, and which is in what how much you will see each of these. And a double Fourier transform gives you the scattering law of the dynamical structure factor. Okay, so we'll take now a few examples of and as we go on, and there's some more quantities that we can. So this I had already shown you the dynamics of organic molecules in zeolite, what they really mean for this I had shown you earlier. So you have zeolite cages. These are large crystalline materials in which you have large cage-like structures, empty volumes, and through which other smaller molecules can diffuse through. And the diffusion is somewhat selective, because you need to have some compatibility between the size of the molecule and the empty space available. And there are a variety of theories. Sometimes you have a resonance effect or otherwise. But in any case, neutrons are ideal probes to study this. And there are a variety of diffusion processes possible. You can have diffuse a very slow diffusion, or you have one time scale of diffusion in which the atom may be just moving around inside it. You can have a, but just translating around, or you can have a, just at the walls, for example, or it could be at the next time scale. You can have a diffusion inside the cage, and another time scale you can have a diffusion through the cages from one cage to another, and so on and so forth. So these particular details were done using molecular dynamic simulation for a particular molecule. And what one finds is that because of the variety of dynamics possible, so okay, this is just the correlation function in which already one Fourier transform has been done. So it's intermediate, what I mean was this term, the incoherent single particle, incoherent intermediate scattering function, one Fourier transform from the self part of the position time correlation function. Okay, why incoherent is because here the much of the scattering comes from the hydrogen atoms that are part of these organic molecules, and therefore most of the observable neutron scattering would be in the form of incoherent scattering, and therefore we just focus attention on the self part of the correlation functions. And so this is a typical, and now again, as I said, it's possible to actually calculate it only for specific Q values which are consistent, as I said, with the simulation's size of number of atoms for the simulation box. Okay, so within that simulation box, whatever wave vectors you can form like standing waves are allowed. So for those values, calculations are done. And okay, it appears obviously it's a decay function. It has to decay with time because it's stochastic in nature. However, this could not be fitted with a single exponential function, but rather it's found that you need to fit with at least 3 Lorentzian functions with certain amplitudes. So that was actually done, and then this is how you get. So as a function of Q, you get this, you have the 3 full breadth at half maximum, or rather the three relaxation times, which are a function of capital Q also. And so you can see there are three types of dynamics possible here. And as we said, only one of these 3 was close to what was observable using a particular spectrometer, because now you can see that these are at very different scales. You have something like of the order of 1 milli-electron volt, so you need a relatively slow, relatively fast dynamics, and you have the slower dynamics, and this is much slower dynamics. So this is of the order of 0.1 milli-electron volt, matches with the energy resolution that is available at the Dhruva reactor. Other time scales could be seen at other high resolution spectrometers at high intensity machines or high flux reactor or spallation neutron sources. Okay, so this was just an illustration that you have to do in the molecular dynamics simulation, get the position time correlation function, do a Fourier transform, and then see whether how it can be fitted with a single Lorentzian or more Lorentzians, or sometimes even with a not a Lorentzian but a not an exponential but a Gaussian kind of term, and so on. So yes, that is a modeling of what is simulated, and then you can compare with experiments. It turned out to be a very good agreement here, which shows that the classical force field that was used here was quite good. And yes, this is another thing which I told you, which I'm not going to give example, but this was also calculated from molecular dynamics simulation. So the actual dynamics involves rotation as well as translation. Okay. Another quantity that we can easily calculate is the standard time averaged pair distribution function. So this is just let's say how many atoms are at a given distance r, or the distribution of pairs of distances, distribution of the distance between pairs of particles. Okay, so Nij is the average number of atoms of let's say species J around a species I. So well, okay, it's a way of putting it, but it is just how many atoms are there of type I and J which are at a distance r. Okay, or at a between distance r and r plus dr. So because nothing is there at exactly a very fixed distance, there is always a distribution, and so that will obviously depend on what is the shell that you choose, and it's can be normalized with the what is number density in a simulation cell. Okay. So this is a pair distribution function, and this is directly related to the what you can calculate by also what you can measure by elastic neutron by just a diffraction. Okay, the Fourier transform of the G of R gives you S of Q, which is just a structure factor observable in diffraction. Another quantity you can calculate is the velocity autocorrelation function. So it is a self-term velocity autocorrelation, the correlation between the velocities of the same atom at two different times. Okay. What is the power spectrum, which is, so this is a classical power spectrum or frequency spectrum, and this is directly related to the things like phonon density of states. Okay, but it's also related with the diffusion. So this is just the frequency distribution of the atoms in your simulation. Okay, another quantity that we calculate is the mean square displacement of displacements as a function of tau. So it's again just yes. So for the same atom I, how the distance, how the distance between its position at time t and time tj and time tj plus tau. So what is the mean square displacement over a time tau, and you sum over the certain number of time steps as well as the number of different atoms, and normalize it with the total numbers involved. So this is simple to understand, the total mean square displacement of as a function of tau. So if I show you this picture, you would easily understand. Okay. So this is certain simulation done in a typical solid sodium silicon oxide, sodium silicate, and what you can see here as a function of time, the mean square displacement of these three kinds of atoms, oxygen, sodium, and silicon, are plotted. Yeah, initially at zero time, the mean square displacement is obviously zero because the atom is where it is at zero time. But very soon, as the vibrations take place, you reach an equilibrium value over a fairly small time, and so then these are the equilibrium mean square displacements, which is what you are familiar with, the mean square displacement or the de Broglie factor which you get from diffraction for various atoms, as or the thermal ellipsoid or the thermal amplitude. Various names are given to it. So this quantity can be calculated. In fact, you can calculate the same quantity also from lattice dynamics. Usually, if you have all the phonon frequencies available, then you can calculate what is the mean square displacement of the atom. So at low temperature, this is what happens. Okay. At 300 K, so typically this number may still be different from lattice dynamics to the extent that lattice dynamics includes a 0-point energy, whereas this one does not. This is a plain classical term, However, just certain constant values at as a function of time is an indicative of there are no diffusion, nothing, and there is just an equilibrium quantity. However, this particular system is known to have some diffusion of sodium at high temperature. So further simulation was done at higher temperature, and then you can see that at temperatures like 800K or 900K, the oxygen and oxygen atom denoted by the black curve and the silicon by the green curve, these do not change with time after the initial equilibration time. Okay, we call this, this is equilibration time, time over which typically, let's say 1 or 2 picoseconds. Only after that you get equilibrium values. Before that you have a lot of memory of the initial state. So that remains. So you got the U square of the sodium atom increasing with the time, and this linear increase is a simple manifestation of diffusion. Okay, in diffusion, if you have a diffusing particle, the mean square displacement is proportional to time itself. Okay, so and the proportionality constant is related to the diffusion coefficient. So the isotropic diffusion coefficient can be determined by mean square displacement at time tau divided by 6 times tau. This comes from U square is actually over 3 degrees of freedom over the 3 directions, x, y, and z, for example. So that, and then a factor of 2, it's just part of the diffusion equation. So this is, so you can calculate the isotropic diffusion coefficient. So actually we would just take the linear part here, ignore the initial equilibration time, and then get the slope of these curves, and the slope of these curves will give you this quantity. There are some things that we need to be concerned with, like how long the simulation has been done. Here the simulation was actually done beyond 20 picosecond, but the plot is given only this, because if you suppose my simulation is done for only 20 picosecond, then what happens is that the values calculated at high time will see, for example, the values that we have calculated here, for example, at 10 picosecond are averaged between, say, time 0 and 10, also between time 1 picosecond and 11 picosecond, or between 2 picosecond and 12 picoseconds. This is just a time difference, not necessarily when my simulation actually started. So because I need to do that kind of averaging also, average over the simulation time steps. So that's why I actually have to do simulation somewhat longer than what I'm interested in. But anyway, the important thing here is that if you get a linear region, then you can very easily calculate the slope of that plot and get the diffusion coefficient. You can also work out anisotropic diffusion constants along, say, 3 different mutually perpendicular directions. And so these are the anisotropic diffusion coefficients. And the diffusion coefficient is also possible to calculate using the velocity autocorrelation function. So that is just the value at at corresponding to the So it's essentially an integral over the velocity autocorrelation function, which means what is the average autocorrelation. Okay, so if it's a diffusing particle, then its velocity at 0 time and very large time will be correlated, because it's there is a net displacement of the particle. So along that direction, you can expect a correlation. So this is more rigorously also shown that you can get a diffusion coefficient this way also. Okay, now that's pretty simple. You have the got the diffusion coefficient. If you get it as a function of temperature, then this could be related with the activation energy of this diffusing process. So you can obtain the activation energy and by fitting your numbers. So, okay, this is a linearized version. Log of this quantity, you have a linear plot. So, for example, okay, this is just a diffusion coefficient calculated as a function of temperature, and this is a linear plot. You plot 1 over temperature against the logarithm of the diffusion coefficient, and that has that. Well, you can see it's not a great fit with a straight line. Could be for two reasons. Your process may not be a simple activation process with a single activation energy, or more likely, there are simulation errors or limitations. So these numbers, they may have error bars because of the finite simulation size, both in terms of the simulation cell size as well as the simulation time, limited time. So various limitations, but all the same, it gives you a somewhat linear plot, and you can calculate an activation energy by fitting it to a straight line. So this is a typical number, about half an electron volt. The same simulation was done with this is the ab initio method, also done with a force field. So this will be of course limited by what kind of force field you actually use. And in ab initio calculation, again, although we call it ab initio, it's accurate, but all the same, ab initio calculations also you are forced to make certain approximations because you don't have infinite computer resource. So you will always apply some certain cutoffs in calculating your total energies or the basic various quantities. So there are limitations, what kind of pseudo potentials you use, or how long, how much you, and again various time steps. And the number of approximations are always there, in which you keep refining, but you're forced to make approximations largely because of the limitation on the computer resource. And also, this simulation can be done with only few tens or maybe 100 atoms, whereas this simulation is done with a much larger number of atoms possible. So you have got quite a linear term here. But all the same, these two methods give consistent activation energies of about half an electron volt, which is quite reasonable. If you plot actually the diffusion coefficient as a function of temperature, yes, below certain temperature, your diffusion is practically not observable at simulation time scale. It may be much too slow, so you can't see it. But beyond the temperature, you begin seeing it. So it's actually a diffusion of sodium atom in this material. Okay, so now just I'll give a little bit more about this particular study of sodium diffusion in this superionic conductor I just showed you example of. Actually, in this structure, this has a orthogonal crystal structure, but when the crystal structure is so perfect, the possibility of allowing diffusion are limited. Quite often, if you have a perfect crystal structure, no vacancies or no defects, then the diffusion is going to be negligible. The moment you have some defects, like some vacancies, then some of the atoms can diffuse from the lattice sites to the vacant sites, and so on. It goes on. So the diffusion can be initiated the vacancies or around defects. Is analog. So there is also an amorphous silicate, and so in that structure, diffusion is actually observed. It's not observed in the crystalline space, but so you can simulate an amorphous structure. The normal standard procedure is that you may start with a crystal structure, but you simulate up to very high temperature beyond the melting point, so that the atoms don't remain localized to their lattice sites, but begin having very large thermal amplitudes, and then they leave the lattice sites. And so in a way, you have a structure which is liquid-like. You may have to increase the temperature significantly above the melting temperature. And so then you have a liquid structure, and then you kind of deep freeze it. rapidly cool it with a reasonable reasonable cooling rate, so that its simulation is still stable. So that way, you cool it, freeze it down to very low temperature, you get an amorphous structure, which is essentially the a frozen state of the liquid structure, but somewhat relaxed. Okay, in a liquid, each atom is not at the minimum of the, not at a local minimum of the energy, whereas in the amorphous structure, the atom would be at a local minimum of energy at very low temperature. Okay, so now in such a structure which is full of variety of defects, in a way, so you can get diffusion. And what we actually identified is that because now the structure is amorphous, and the silicate polyhedra, they have a variety of different orientations, and that enables the sodium atoms to diffuse through them as you increase the temperature. So this is because of the correlation with the neighboring orientations of silicates and so on, and the overall amorphous structure, diffusion is enabled. Okay, so these are the this is just now you can see the mean square displacement of is calculated for the sodium atom. See, what I earlier showed you was the time average of okay, see, this was average over all the sodium atoms, so you get a linear term. Okay, however, if I look at the individual sodium atoms, then is not is different. Like it has a fairly low mean square displacement, and then suddenly it jumps over, so and acquires a larger mean square displacement, which means the sodium atom has actually jumped from one position. See, this is the mean square displacement is changed by something like 6 Armstrong square, which means it is jumped by about square root of 6 is about 2.5. So there is a jump of about 2.5 Armstrong, and that is shown. So this is one particular sodium atom as shown this picture. As you increase the temperature, several sodium atoms show the such jump motion. So this is just a direct illustration of the jump dynamics, and you can see the jumps are actually the jump time is negligible compared to the stay time. The residence time is much longer, and the jump time is more like just a very few vibrational periods. So this is in the range of only a few femtoseconds. Okay, whereas the residence time runs over several picoseconds. So neutron scattering would actually see this. These jumps are practically instantaneous on these time scales. Okay, so now this is again, so using those quantities, one goes through all the calculating the position time correlation functions and the intermediate scattering functions and the dynamical structure factors, and then you can calculate what are the half width at half maximum as a function of, for example, in this case the wave vector, and that shows certain behavior. This could be fitted to these diffusion models that we had talked about. So using those diffusion models, you can fit it, and then you can find the equivalent of what is the jump length. So in this particular case, this model, Paul-Ross model fits better, not perfectly, but it fits better, which is actually corresponding to a Gaussian distribution of jump lengths. The jump lengths are not fixed values. In the other model, that assumes fixed values of jump length. So a fixed jump length model is not working here. A fixed jump length model usually works much better in a crystalline structure with the defects. That means the atoms still jump at a fixed by a fixed jump length corresponding to the lattice and the vacant sites, between lattice sites and vacant sites, for example. So that model is more useful for crystal structures. This model here, we can see, works out better in an amorphous structure where the diffusion length has a distribution. However, this comes around as I said about. So this diffusion length or the jump length is still related to the typical first neighbor distance between two sodium atoms, which is of the same order. And the resonance time is again of this order, about 15 picoseconds, and you get a diffusion coefficient. I should say that in this calculation, the calculation has been actually done at high temperature because at very low temperature, the diffusion coefficients are much less and beyond my simulation time scales. And therefore, I'm purposely doing it at higher temperature where I can get this, I can observe the diffusion. So I would be overestimating the diffusion coefficient, or I would be getting the diffusion coefficient at high temperature. But I will be able to get what are the nature of jumps, what are the jumps diffusion pathways, and which I can also get then related to neutron scattering. These are neutron scattering data taken at the spallation neutron source in United Kingdom, and which has a resolution of 27 microelectron volts. This is compared to about 200 microelectron volts that we have at the Dhruva reactor. This is a high resolution spectrometer. In fact, other spectrometers at the Oak Ridge National Labs have even better resolutions. So even at this resolution now, we have seen diffusion not at room temperature. At room temperature, you get standard delta function, that is elastic scattering, brought with the resolution, that is the resolution of the instrument. But compared to the resolution, we see, so if the data is fitted, at higher temperature, you can see the extra broadening of the elastic line here, and the extra broadening is then fitted to a Lorentzian function. Okay, and you get the Lorentzian half width at half maximum. Okay, so then this one, this can be plotted. You can see there's a lot of noise in the data, and that's because in this particular case, the scattering cross section of the sodium atom is relatively, is much less than what you typically are, you know, about the hydrogen atom. We said it's almost an order of magnitude less. So these are extremely difficult experiments. So far, less than 10 such experiments have been done on battery materials like lithium or sodium battery materials in which diffusion is of interest, and but one is able to find get information about the diffusion pathways and diffusion timescales in these materials. So with this, I should thank you today. Yeah, I think we are done. And next lecture, we will go into some more, maybe a tutorial kind and some other things. If there are any specific questions, please let me know. Yes, hello?
No question yet, sir.
Okay, we'll wait for a couple of minutes, otherwise we'll close it for today.
Sure, sure.
So there was no further interruption, right? I think it's okay.
No. Everything was fine, sir.
Okay, thank you. Okay.
There is no more question, sir.
Okay, thank you very much. Thank you, everybody.
Okay, sir. Thank you.
Thank you.